this asynchronous hybrid squids and quickly introduce you so the experimental setup and the results, and then conclude. So first of all, for the DC squids, we all know about the DC squids. It's a superconducting loop containing two gelatin junctions. The superconducting loop is, of course, flux quantified by phi naught. And we are exploiting the Meissner effect, which translates in a screening current when we apply any external flux to this superconducting loop. And there's an important design parameter, which is called the beta L, the critical current modulation, which need to respect some standards. So I just quickly present you the schematics with these two junctions and the loop. And you can see that the bias of the DC squid just splits the squid in two. So this is the case of a symmetrical DC squid. So how does this DC squid work? We are using actually two identical junctions, which are overdamped. Here on the simulation, I present you the IV curves on the left, and on the right, you have the voltage flux characteristic of the squid. So basically, you can see that when we do not apply any flux to the squids, we obtain this blue curve, which is basically the highest critical current can reach. As long as you input flux in it, 1/4 of the phi naught, you can see that we are approximately at 65 microamp critical current. And when you put half of a phi naught of the squid's of flux inside the squid, you reach this 40 microamp critical current. And so basically you modulate the critical current thanks to external magnetic fields. So now imagine that you bias your squid to, for example, 60 microamp, like this rose arrow. And we can see that if we maintain this bias current at 60 microamp and we apply external flux, we obtain the characteristic, the voltage response on the right. On the bottom one, the black traces. When you increase a little bit the biasing, for example, at 2 times IO, IO is a critical current of a single junction in the squid, you obtain the red response. And how we use this squid, we can see that it's clearly a nonlinear periodic response. We basically just take the point where we have the highest slope. So for a small variation of flux, we have the highest voltage change response. So basically, how can we do that? We use this basic electronics, which is called the flux lock loop, which basically lock this working point at the optimal part, where we have the optimal slope, and which maintains it. So this electronic basically allows us to have a very, very linear response. And it has, the problem is that it allows us a really nice sensitivity in magnetic flux, but it has a slew rate which is limited by the cable length, basically, which limits the setup to work at few tens of megaphi naughts on the best case. So now let's switch to this digital squid, this asynchronous digital squid. For this asynchronous digital squid that you also saw on, this morning on the presentations, is basically a bidirectional RSFQ-based squid. In this case, we are not biased over the critical current of the junctions, but under the critical current of the junction. And when you apply a flux on this flux input, you basically digitize the signal, and the digitization step is phi naught. For any RSFQ cells, it's always the same. And the biggest advantage is that depending on the fabrication process and also the complexity of the digital circuits you're building with RSFQ cells, you can reach 10 gigahertz and a lot more for very simple cells. So we know that the slew rate of this squid is basically limited to by the shunt resistors we have in parallel of the junctions in order to damp them, and it basically brings us to gigaphi naught per second. So we can clearly see that in the digital squids we have a very, very high slew rate, which can directly translate in a very high dynamic. But the sensitivity, basically the digitization step, is only finite, whereas before on the DC squids, we were in the range of microfinite. So here, how does this asynchronous squid works? You already saw the simulation this morning, so I'll be very quick. Basically, here the green ramp up and ramp down is an external signal that we apply to the squid. We input flux, and we can see black pulses on the middle part of the screen, which basically is the response of the junction number 1. And on the right side, we have then when the slope decreases, the junction 2, which switches, so it emits this red pulses. And underneath, actually, what I put, this step-like signals, is the already RSFQ processed output of the negative and the positive channels. And so basically, it's just, it allows us to read out at ambient temperature the internal states if we had a pulse emitted or not. So one important part is the current which runs in the squid loop in blue. We can see that despite the fact that we increase the flux, the external flux, we input high input flux, it is limited. We have a maximum range it can attain and a minimal range. So this translates directly by the fact that the superconducting loop is quantized. So what is the idea? We know that the DC squids are very sensitive, but the slew rates are a few megafinite per second, and it requires an external feedback electronic. On the other case, the asynchronous digital squid has a sensitivity which is not that good, a finite, but the slew rate is really, really high, simply because of the RSFQ electronic architecture. So, and the electronic is very simple. So basically, we just make a hybrid sensor. We add the two of them, and this hybrid sensor has a sensitivity of a few tens of microfarads, a slew rate of several gigahertz. So it's all theoretical, of course. We will see an on-chip locking of the DC squid in order to operate the DC squid on the best region, and a very simple control electronics. So here is a very basic way to do it. This schematics shows us how we do it. We basically just couple a DC squid to the loop of the digital squid. The DC squid here operates as a simply, we can see it as a current probe. It's a flux probe, basically. It basically observes the flux running inside the loop of the digital squid. It's weakly coupled. It has its reasons, we will see. And we will see that these structures allow a local feedback, because we saw before that the current running in this digital squid's loop is limited, and you have a minimum and maximum. So basically, you can, as the DC squid only views the current running in the digital squid, it is locked by the digital squid. So here is how it's locked. On the bottom right, we can clearly see the V-phi curve, and we know that the current running in the digital squid loop is limited, so you have a range of flux allowed, and by smartly coupling it, smartly biasing it, you basically choose a range in the V-phi curve on which the DC squid basically responds to external flux. So the coupling factor here, basically, I told you it's 1 over 15th. And the reason is, if you want to still, as you do not lock on a single point on the V-phi curve, like we did on the classical DC squids electronics, we have a nonlinear response. And the nonlinearity here, it's quite high, but we can basically process it by software later on after the acquisition, because we clearly know the characteristic of the DC squids. So here is a simulation about how this whole hybrid squid is working. So on the green, you have the injected current on an external antenna, which is a flux coupled to the squid. And these blue steps are basically the signal that we can reconstruct thanks to the SFQ pulses output. And on the bottom part, we can see the black traces are the voltage responses. We can clearly see that it's not perfectly linear. we are clearly running on the V5 characteristic of the squid. It's not perfectly linear, but it's quite good, and it allows us, in between all these digital steps we have in blue, we have a lot more information and we gain sensitivity. So we increase the sensitivity of our squids. So how are these hybrid squids measured? Here's the setup I used. This is our lab in France. We have a GM cooler with a 405 milliwatts cooling power at 4.2K. And we also characterized this cooler, and at the 4K plate, we saw that the DC motor of this cryo cooler basically induces around 80 to 110 nanotesla of 1 Hertz signal, which is directly linked to the piston's movement underneath the cryo cooler. So here is a picture of the 4K plate. On the middle part, the green PCB you see is a chip holder which operates unshielded. On the bottom part, the black holder you have is basically the chip holder for shielded environments. So the shield in this case is basically lead that I pinched by hand and put just on the top of the chip. So what does it look like when you translate it to an actual circuit? So here's a picture of one of the 9 hybrid squid we designed in the team. So you have the green square with all these branches, which is the antenna, basically. Around it, you can see a brownish trace, which is basically the excitation loop on which we can input current in order to couple flux to the antenna. And you have on the middle part kind of colored points, which are basically the RSFP cells. So these cells were basically assembled by the Turkish team at Ankara TOB, and we handled all the analog and the antenna part. And the routing of the chip was also done by Sasan Razmika, which was back in time with us, but is now with Ankara TOB University. And the chips are fabricated with the Japanese process, STP2 at 2.5 kiloampere per square meter. And centimeter square, sorry. And there is on the digital part a 3-bit asynchronous counter for both positive and negative signals. So here is a measurement on hybrid mode. We can see that here I injected manually a current source. This on the top side, the orange line is the current I injected. The small steppish blue lines are the reconstructed signals that we obtained thanks to the digital outputs. And really on the bottom, the lowest curve shows us the voltage response of the DC squid, which is coupled. And we can clearly see that it looks like really like a triangle. And we will see that when we combine the reconstruction of them, we have here the spectrums. And we can clearly see that we have information in between the digital steps, and it operates actually quite well. So this was to prove a proof of concept of this hybrid squids. And we went, so the key experimental results of a few samples we measured is basically dynamic range. Dynamic range is, it means that the maximum excursion you can measure on the signal. So how much finite peak to peak of signal it basically measures correctly. So the maximum dynamic range we had corresponds to a bit more than 7,000 finite, which correspond to approximately 60 microtesla. The slew rate we measured with 100 kilosample per second is 72,000. Actually, here we can see it proves us that we have a small problem, which is basically the noise of the bench, which induced jitter. And our sampling rate was basically not fast enough to catch all the pulses. So the slew rate we measured was not really the real slew rate, as the sensor himself is really asynchronous and can go up to easily tens of gigafinite per second. So the flux noise we measured was 150 microfinite, and it really is a lot more than what we were expecting. And the main reason of that, after a careful calculation, we found out that our bench was basically too noisy, and it was not the sensor's noise level himself. So here is a measurement that we recently performed. Some of you might know it. There was a solar eclipse on the 10th June, and we basically acquired the Earth magnetic field signature at this date in LSBB, which is an underground laboratory providing exceptional conditions to measure. And they also have a commercial DC squids to probe the Earth magnetic field. So here we can clearly see that at French time, around 11:30, there was a peak. And this was also about the time that the eclipse was optimal. So this trace is actually quite reliable. We compared it with what they acquired with the commercial squid, and we can clearly show that our sensors are operating quite well, even over a long time of operation. And this signal was built not with the digital signals, but only with the analog DC squids trace, and reconstruct the digital step-ups thanks to signal processing. So in conclusions, we measure the sensitivity, which was limited by the bench and not by the sensor himself. Sorry. So we are actually improving the bench by building custom electronics, control noise electronics to bias and to measure all this digital part and analog part. We measure the slew rate of 72 kilo phi nuts with only 100 kilo sample acquisition frequency. So it was also basically limited by the bench himself because of the noise which induced jitter. And the maximum dynamic range actually we measured of 12.9 bits corresponding to a 60 micro phi nut, 60 microtesla, shows us that our RSFQ, so our logic cells, stops operating because of the effect of the magnetic field. So in order to basically avoid that, or limit at least the effect, we need to design custom RSFQ cells which are shielded and less sensitive to external magnetic perturbation. We also saw that simple signal processing allows us to retrieve the measured signal from the DCA squids output only. And a very long time acquisition actually proved also that our H squids are operating in non-shielded environment quite well too. So I would like to acknowledge the Fonds Européen de Développement FEDER, which partly funded the job, the French Space Agency, which funded my PhD, and the French-Turkish Partenariat Uber-Curien and the Bosphore project. And also, I'm grateful to Professor Fujimaki and his team to kindly provide the Connect library, which we use for the digital part. Thank you.